1.5, limit of a functions. So in the previous sessions, we sort of get an idea of how the limits will work and then what is the limit talking about when we are looking for the slope of the tangent line. Right? It's basically we trying to estimate, the point closer and closer, closer and closer to see what is the values coming up. So to reiterate that, to making sure that we understand the limits of a functions, right? I want to illustrate something. Let's say, if I throw a marker to the wall, right? And a marker right here, pound, and then it dropped down. So the questions that I can ask you is, did the marker touch the wall? Okay. And if your answer is yes, you are right, right? But however, if we look at from the point of position function, that is basically, I can use this, dotted line as my model. It's look like more of like a little bit of a quadratic model. So I can talk about the positions of the marker, right, at a certain period of time, t. Right? And therefore, at this particular time, the marker will touch and then it will hit the wall. But if I look at, if I want you to look at from the point of view of limit, okay, of a function, then we can argue a little bit this way. Right? From here to the wall, we have this distance, right? And I can talk about the midpoint of the distance. From this midpoint, I can talk about another midpoint right here. And from this midpoint to the wall, I can talk about another midpoints, and then so on and so forth. So notice that it's going to be like, infinitely many, right, cases that we can, midpoints that we can talk about. But would that be an end? Would there be an end to it? The answer is no, because we can talk about what between any little two distance, I can always talk about the midpoint, and then from that midpoint to the end, I can talk about the midpoints again. Okay? So that basically, sort of illustrate and then talk about the idea of the limits. The limit is basically when we talk about the limit of a functions, okay, the limit of a function in this session is basically talking about a value when, the x value is getting closer and closer to a certain number, and what is the outcomes going to be. So that is a big difference between the function value and the limit value. Once again, the limit value that we are talking about is trying to look at, when the x value is closer and closer to a certain value, is there going to be what? A limit or not? Meaning, is there going to be an outcome? So going with this idea, let's go back and then talk about the function that we saw last time, right, on finding out the slope of the tangent line. But this time we want to talk about just straightforward from the function. Okay. So if you look at on this function x squared plus 2x plus 2, again, when the x value approaches to 0, and we know that if I plug it in 0 into this functions, my value, because x squared will go to 0, 2 times x is 0, so it will be what? 2 right here. That is the function value. But the idea of a limit is different. The idea of limit is if I pick the number x, right, the value of x that is closer and closer to 0, what is the output's going to be? That's the limit. Okay. So here's the illustrating a table of value that I pointed out. When x is 1, my y is 5. When x is 0.5, my y is 3.25. And notice that my X value is smaller and smaller, which means I'm trying to getting closer and closer to 0. And what happened to my output value, if you take a look at it, the value is starting with 5 and then getting smaller and smaller, but however, it stopped, sort of like steadily closer and closer to what? The value 2, as I can see. Right? If I make it a little bit smaller X value, then you can see that a number that is, the output value is much more closer to the value 2. So this is from the right-hand side. Okay. So this table of values sort of shows you, X approaches to 0 from the right. Now, let's take a look at on the other case. X is -1, and then keep on going until what? It getting closer and closer to 0. So again, X is approaching to 0, but however, this times you can see that it's -1, -0.5, -0.1, so on and so forth, and then getting closer and closer to 0 from the left-hand side. So the X value is getting closer and closer to 0 from the left-hand side. And what happened to my Y values? A -1 is 1, -0.5 is 1.25, and then keep on, increasing. And then as you can see, as the X value is very, very close to 0, right, from the left-hand side, my output value is very, very close to 2, 1.99, and then it will be like 1.999 something. So this table of value representing X is approaching, right, approaches to 0 from the left-hand side. And what happened is what we, found out is both of them is trying to getting close, both of the output value, either from the right-hand side or left-hand side, is getting closer and closer to what? The 2, right? The output value, the Y value 2. So this is the idea of a limit. That is the difference from a function value. A function value is basically you have a functions and you're going to be inputting X and then there is an output, right? And there is output. And we call that the functions defined. But as in limits of a functions, right, the value that we are interested in is not what is a solid number. Where is that approaching? From both left-hand side and the right-hand side. Do they approach it to the same value or not? So what I illustrated in this table of value, in terms of notation, we write it like this. Limit as X approaches to 0 of the functions X squared plus 2X plus 2, and the limit value is 2. Because as we can see, that is what getting closer and closer to 2. And this is a way of computing limits by inputting, looking at the numerical data. And then we're going to look at, how to get the value of the limits by looking at the graphical approach. So I also illustrate with the graphical approach what is happening. As X approaches to 0 from the right-hand side, the Y value is approaching to 2, right? These directions. And then as X approaches to 0 from the left-hand side, right? The Y value approaches to 2 also. So in general, the way that we write it down is limits as X approaches to a value A, right, of functions. If that's have a limit, meaning the left-hand side and right-hand side approaches go to the same, number, then we call it, there's a limit L. So this is basically like, sort of like tracing idea, try to find out, using numerical data to find out the value of the limits of a function at a certain point. Okay. So let's investigate another example. And then after that, we're going to talk about what is the pros and cons of these. We want to take a look at it. The next example is finding out the value of the limit as x approaches to 0 of the function sine x over x. And notice that in the previous example, f of 0, I should say, since it's y, I would say y of 0, we do have what? 0 squared plus 2 times 0 plus 2, which is 2. The function's defined, okay? But if you look at on this example, let's say my functions, right, is sine x over x, but I cannot find out f of 0 because that will give me sine of 0 over 0. I know that sine of 0 is 0. 0 over 0, what is that value? We don't know. We haven't talked about it yet. It is called the undeterminate form. Right? There's a terminology for it. Right? There are many undeterminate forms, and this is one of them. And you will see more in Cal 2. So now the question is, now I know the function does not define at 0, but what about the limit? Now, here's the clear illustrations of the difference between the function value and the limit value. We already know the function does not define at this point, right? Because there's no output value. But however, it may not be true for the limits, okay? Because the idea of the limit is not looking for where x is exactly at 0. We are looking for when x is approaching to 0, meaning when x is getting closer and closer to 0. What is the value that we're going to get? Okay. So clearly, if will be graphing this function, sine x over x, there will be a hole on when x is 0, meaning there will be a hole on this y-axis. But the question is, where is that hole? In pre-calc, we talk about the linear rational functions, such that if the rational function is something like this, 3x times x minus 1 over x minus 1, if we can reduce it the same factor and then simplify it, then we know that there is a hole at x equal to 1, right? We talk about that. But in this, and then we will be able to find out where that hole is, right? That's basically what? 1 f of 1, that will be what? 3 times 1, that will be 3. Okay? So, but however, in these situations, right? In this situation, there is no way that we will be able to find out because I got this situation 0 over 0 and I cannot simplify any further. So this is where we want to use this limit idea to find out and then graph this. So let's take a minute, okay? Pause it and let's take a minute and then use your calculator to find out the value of this. So when x is 1, what is my function value going to be? Which means sine of 1 over 1. Make sure you are in radian mode, okay? And then similarly, you can find out the other one also. So pause it for a second, a minute or so, a few minutes to evaluate those, and then let's try to investigate this, what's going on. So after calculating with the calculator, we got these following values. Hopefully you get the same. But the point that we want to see is this. One is output is about 0.8, one is 0.5, the output is 0.95, and then as we get x value closer and closer to 0, and notice that my output value is getting closer and closer and closer to 1. Okay? But we know that the function does not define at 0. Now, you can try to use a calculator to find out the other sides, or you can also think about this, what we talked about before, right? If I substitute x with negative x for the functions, then I'll have sine of negative x over negative x. And that will give me, sine is an odd function, so therefore it will be negative sine x over negative x. When I reduce this, that will become what? Equal to sine x over x, which is original functions. So this is basically talking about the even functions right here. So the even functions are symmetric about the y-axis. So therefore, I don't even need to look for the value on the left-hand side. If it is an exact value, it will be what? Exactly the same output that we're going to get. So from here, what we can see is, when x is approaching to 0 from the right-hand side, right? And then the value, the output value is what? Getting closer and closer into 1, right? And when x is approaches to 0 from the left, and since this is a symmetrical, so it will be also getting closer and closer to what? The same unit, so 6, 9, and then what? 8, 3. So that sort of tells me now, I can sort of say that the limit as x approaches to 0 of sine x over x, that is equal to 1 by analyzing this numerical data from the data of values. Therefore, for the graph part, I also know where exactly the hole is going to be for these functions when x is equal to 0. See right here, the function does not define, so we don't know where exactly it is. But from the limit value, we can see that when x is getting closer and closer to 0 from the left-hand side and right-hand side, the limit is what? 1. So that means the hole will be at 1 right here. And then from here, we can graph it because, at 1 will be 0.8, right? And so I'm going to continue counting like, 0.5, which is right here. 0.5 is about, 9.5. So it'll be about right here. And then it's getting closer and closer and closer to 1, right? So that's what we found out right here. And since this is a symmetric, the left-hand side and right-hand side is the same. So I can sort of graph this. And it's not really a good thing to graph with this notepad right here. So it will be something like this shape, right? So this is one way that we can use the limits. And then this is a very beginning idea of how to find out the limit by numerical, right, methods, which is, find out the table values and then looking at where it's going to be approaching to. So from these two problems, right, and we know sort of getting an idea the difference between the limit value and the function value. Now let's take a look at the next example. So if I look at the next example, right, again, limit as x approaches to 0 of sine of pi over x. And our functions, in this case, is sine of pi over x. And clearly, x cannot be equal to 0, right? That will go to undefined, and then undefined of a sine operator is, we don't know what the value is. So, f of 0 in this case is what? Undefined so far. Right? The function does not define. So, from the previous example, now I want to see that, okay, let me put some values and see what's going on, right? So if I plug in 1, that will be sine of pi, which is going to be 0. When I plug in half, right, 0.5, which is half, that will be what? Sine of pi over half. That will be sine of 2 pi when you reciprocate it. Sine of 2 pi is still, again, it will be what? 0. And if I continue, then that will give me what? Sine of 0.1 is still going to be 0. and then 0, and so on and so forth if you use a calculator. Right? You get all of them 0. Then what happened is right away you might be concluding that, oh, okay, it's approaching to 0 from the right-hand side when we approach it to 0, and then from the left-hand side when we approach it to 0. So right away you might be thinking that, oh, sine of limit as x approaches 0 of sine of pi over x, that is equal to 0. And that's where it's going to be wrong, right? Because this numerical methods is a very good point of view to get an idea of what the limit is talking about, but not to use it to find, the limits because of a weird function, something like this. Right? So let me show you, how this graph going to look like. Actually, this graph is going to look like, oscillating like this. And as you're getting closer and closer to 1, it's keep on oscillating back and forth between 1 and -1. Okay. So there is no, not unlike the other example that we have right here, it is not approaching to, the limit value is not getting closer and closer to one number, right? So it keep on going back and forth. So let's take a look at on that part for the graph of this. So in a graphing calculator, I can basically type it in, y equal to sine of pi over x. So as you can see, how this graph is oscillating. And it keep on, if you enlarge it, it keep on oscillating back and forth, right? One is getting closer and closer to 0, as I pointed out. You can see that it's keep on oscillating. That's why the graph look like this. So the limit never reach it to like a single numerical value. So these are the function values. So in this case, these are like, getting like 0 all the time, right? When x is closer and closer to 0, but however, the limit actually does not exist when we start looking at the graph. So that is a cons of this method, numerical methods, right? It's more of like guessing game. And that's the reason why we want to, in the next sessions, we want to learn how to find the limit of a functions algebraically, okay? So in these sections, now that we got an idea, we're going to focus on how to find the limit of a functions graphically. Okay? So as I pointed out in the example, the previous two examples, when we talk about a limit of a functions, right? We need to consider what approaching from the right-hand side and right-hand side. Only both left-hand side and right-hand side approaches to one number, then we call that number the limit of the functions, right? So being said that, the next example I want to show to you is, let's say I have a functions f, okay? And here's the functions continues to the left and then continues to the right. And let's do this open circle right here. And let's do this on a closed circle right here. Okay? So that basically tells me this function is a piecewise defined function. And from this piecewise defined functions, f is defined at 2 right here, right? Or I can say that, if I put an open circle, f is not defined at 2. Okay? So let's take a look at on this, since I started this way, f is defined at 2. But however, what we want to do is we want to investigate part A as x approaches to 2 from the right-hand side. So here's the notation that I'm going to show to you in advance how to write it down. Limit as x approaches to 2. How do I write it down? Is approaching from the right. It's basically you use the upper subscript on the number by putting a plus sign right here. And that's indicating limit as x approaches to 2 from the right-hand side. Of what? of the functions f of x that we are talking about. So how do we find out the limits of this functions when x approaches to 2 from the right-hand side? And that's where we look at this, right? As we moving the x value getting closer and closer to 2 from the right side, what is our graph reacting to it? So from the right-hand side, we are talking about this portion of the graph, not that one, right? So as we move, along with this graph, as x getting closer and closer to 2, and the function's output value is getting closer and closer to what? 2 also. See that? So therefore, I can conclude that in this case, limit as x approaches to 2 from the right-hand side of the function f of x, that limit will be what? 2. Now, as in the other way around, part B, and we are interested in finding out as limit approaches to 2, right? From, I'm missing a 2 right here, from the left-hand side. So the way that we denote it is limit as x approaches to 2. To indicate that it's from the left-hand side, we will use Apple subscript on the number by putting a negative sign of f of x. So for this case, we are talking about approaching to 2, right? X is approaching to 2 from the left-hand side. So approaching to 2 from the left-hand side is coming from this direction, left side directions, and going this. And when we look at the graph of these functions, then approaching from the left-hand side, we are not touching this graph yet at all, right? We are using what? This portion of the graph. So as x approaches to 2 from the left-hand side, we are going along with this graph. And then where is this graph leading us to? Right here, this value. So therefore, I conclude that the limit, right, as x approaches 2 from the left-hand side of this functions, the limit is 1. So now you can see that from the left-hand side and the right-hand side, the limit values are what? Not approaching to the same number. So therefore, limits as x approaches to 2 of the functions does not exist. And we will talk about more, in later on with the definitions and stuff. Okay. So this is the idea of limits, how to find out the limit value from the graph. So hopefully at this point, you sort of following when we talk about the limits, we are interested in what? Looking at the x value getting closer and closer, what is the output's going to be? So the intuitive definitions of this, right? We will talk about a precise definitions in one sections, but the intuitive definitions of this limit is this. Suppose that f of x is defined when x is near the numbers a. Okay. So what do I mean? What does it mean by the function is defined when x is near a? Right. That's basically talking about what? The function is defined on every x value except possibly at a itself. Right? So here, this is the interpretation of it, because probably this is the first time that you see this way of writing in mathematics. X is near the number a, right? Define near a number a. So this basically means what? F is defined on some open interval that contains a, right? In that interval that contains a, except what is possibly at a itself, meaning it may not define at a itself. Okay, may not define at a itself, and we already saw that the case already. See that? Like this problem, we can find out the function value, right? Very, very close to 0, but not at 0. right? Because the function value does not define us. So continuing this, right, to complete that definitions, then we say that the limit as x approaches to a of a function has a value, which is a number. Okay? So this is the intuitive definitions. The idea is like when x closer and closer to a number, what is the limit value leading us to, or is there even a limit value? Like in this case, we don't have a limit value, right? In this case, we don't have a limit value, and we call it limit does not exist. Because the left-hand side and the right-hand side values are not the same, okay? Left-hand side approach and right-hand side approach are not the same value. So getting into more definitions, right? Now that we see enough, so I can talk about one-sided limits because we have a left-hand side limit and right-hand side limits. If the limit of left-hand side, right, the limit from the left-hand side is the same as the limit from the right-hand side, that means limit as x approaches to a from the left-hand side of the function is equal to L, which is the same number as the limit as x approaches to a from the right-hand side of a function. Then we say that the function has a limit value at that particular point. So limit as x approaches to a of f of x is equal to L. Right? And for only one case, and we call it one-sided limits, and we will see that in some cases we only can talk about one-sided limits. Like for example, let's say my function is square root of x, and if I want to talk about the graph of the function is something like this, right? So if I want to talk about limit as x approaches to 0 of the functions, what is that? See, I don't have the left-hand side limit because there is no graph on the left-hand side. So in this kind of situations, this limit as x approaches to 0 from this function, we can only talk about limit as x approaches to 0 from the positive side of the functions. That's the only thing that we can talk about. And the reason why is because, as you can see, we don't have a graph at all on the left-hand side. So we cannot talk about left-hand side and right-hand side approach. So these are the kind of situation that you're going to get for one-sided limit. Now, the limits value can also go to infinity cases, okay? So what is this? What do I mean by the limits is an infinity? So for example, if I say that, here's a 1, and that is a vertical asymptote for some functions such that f of x is equal to 1 over x minus 1, like a rational function. So clearly at 1, the function does not define, and the limit in this case will not define either. And the reason why is because if I say that limit as x approaches to 1 from the positive side of 1 over x minus 1, then we are talking about what? The x value that is very, very close to 1 from the right-hand side. So that means I can consider the x value is 1.0000001. And if I consider this as 1.0001, then my function value, right, will become what? 1 over 1.00000001 minus 1. Did I have an extra one? 2, 4, 6, 2, 4, yeah, I have 7. So what happening is what? We're going to get a very large positive number because 1.0001 minus 1 is 0.0001. And then the numerator number is bigger than the denominator number. So therefore, I know that the output will be what? A very large positive number. And we sort of, I sort of like guide you through and then talk about this idea in my pre-calc class when we are on this rational functions and then talking about the, the behavior around the vertical asymptote, because that idea is very similar to what we're going to be learning in this limit. So therefore, in this case, I can see that if at limit as x approaches to 1 from the positive side of these functions, then my graph is going like this. So you notice that the output value is a very, very large number. It's endless. So it's going to what? Positive infinity. And the same idea if I talk about, limit as x approaches to 1 from the left-hand side of these functions, then we are basically considering, right? My x value is negative 0.0000001. And so the function value is basically 1 over negative 1.00. Oh, wait, my bad. I made a mistake right here. Approaching to 1 from the left-hand side will be 0.999999, like this, right? 2467. So that is 0.9999999 minus 1. And you can see that it will be a very, very tiny, a negative number right here. So 1 divided by a very tiny negative number, that will give me what? A negative infinity, a very large negative number. So what happening is like, the behavior, connecting back to pre-calc, behavior that's going, getting close to this vertical asymptote from the left-hand side, right? Vertical asymptote from the left-hand side to 1, right? Approaching to 1, that's give me what? A very large negative number. So the limit is going to what? Negative infinity. So therefore, in this case, you can see that, you might be saying that, hey, approaching to 1 from the right-hand side, the limit and the left-hand side limit, they are different because one is a positive infinity and negative infinity. Therefore, limit as x approaches to 1 of the functions 1 over x minus 1 does not exist. Right? DNE does not exist. This is a shortcut that we're going to write later, starting from now. So, is that the right interpretation? Right? Is that a right interpretation? My answer to you is you really have to be careful. Okay, you really have to be careful because of this. Even though you know that it is going to positive infinity or negative infinity when you're approaching from left-hand side or right-hand side, the limits at this point, the interpretation is the limit does not exist. Remember, what is the idea of the limits? We are approaching to a single number. What does that mean by going to infinity? That means if right now, what I'm showing to you is only one scenario of x value. I can choose many, many other x value that is closer to 1 from the right-hand side and closer to 1 from the left-hand side, meaning if I continue adding this 9, then this infinity value will change, right? That infinity is just representing a directions that we are going, not a particular number. So therefore, from here, the limit does not exist, right? Don't get the wrong impressions of by writing infinity, the limit is infinity. No. Okay, no. So that's the very important part that you need to understand, right? So we can only talk about what, in this case, a directions of the limits is trying to go if I approach it to 1 from the right-hand side, or if I approach it to 1 from the left-hand side. Okay? And what can we talk about the limit as x approaches to 1 at this point? Because of the left-hand side limit and right-hand side limit, since in the beginning, it does not exist. And directions that they're going are different also. So therefore, right away, I can say that, does not exist. I can't even interpret it which direction it's going to be going. Now, another example that I'm going to give it to you is at this point, I can talk about the directions of the limits where it's going. For example, again, at 1 right here, here's a vertical asymptotes. And my functions will be g of x is equal to 1 over x minus 1 square, quantity square. So in this situation, what happened is the graph is going to be what? Going like this, right? We graph because of, this one, it will be a positive number, right? The same. But for the negative value that we get from the left-hand side, we know that is a negative value, but when we square it, it will be a positive also. So what we are looking at now is like this situations right here. Let me change this a little bit. Okay. So now we are talking about, let me erase this so that you will not get confused. Now we are talking about, hey, what is happening on this when I square it? So that means I'm going to be squaring this value. And the same thing, a very tiny number, square it, that will be even more tinier number. 1 divided by a tinier number will be still and then positive infinity. But when we approach it from the left-hand side, it's 0.99999. So I'm going to get a negative value right here, right? But however, this time I'm changing the function of the denominator square. So when I square this, the negative value become what? A positive value, because when you square a negative number, it will become a positive. But it will be a very tiny positive number like before. So it will be what? Again, it will give you a positive infinity. Right? Again, the infinity does not tells you what is the limit. The limit does not exist at this point. It only tells you the directions of the limits can go. But because of the left-hand side directions and right-hand side directions are the same, then I can sort of say that the limit as x approaches to 1 of 1 over x minus 1 square, it can talk about the directions of the limit. I will not write down does not exist anymore. I can sort of guiding where the direction is going to be going. Right? So this is the idea of limit infinity limits. Okay. So now what we can do is we can relate this to what we learned in algebra, right? For vertical asymptotes with the limits. So the way that we read right here is limit as x approaches to a of a function. The limit is equal to what? Infinity or negative infinity. And I'm give you an example with the rational functions, which is where the vertical asymptotes are, right? So like now I can look at, the calculus approach to talk about this vertical asymptotes. If the limit as x approaches to a number a of the functions, and that limit value is either positive infinity or negative infinity, whether it's approaching from the left-hand side or right-hand side, then right away we know that there will be a vertical asymptotes at x equal to a, right, for this particular function. So that's how we can define it, using the calculus idea for the vertical asymptotes that we talk about in algebra. So, and clearly the vertical asymptotes, the function does not exist, the function does not define, and the limit does not exist. And read it properly, okay? Functions, if there is an output, we call it functions defined. If there is no output, we call it the functions undefined, right? Or not defined. But for the limits, we will say that the limit exists or the limit does not exist, okay? So now what we're gonna do is we're gonna look at a graphical example and make sure you use the point that I'm gonna give it to you and then try to follow the graph, okay? First, you put these points, okay? Make sure it's open circle, open circle, open circle right here. And then the rest is what? A closed circle, right? at those points. And once you've put, after you put all of this point, then try to draw the graph the way like this. Okay. So make sure you draw this shape of the graph. Then what we're going to do is we're going to try to answer the questions, right, using this graph, which we will name this piecewise functions as J. So let's move on. The first question is, as limit as x approaches to -3 from the right-hand side of the function J. So where is the -3? Here is the -3. And we are trying to approach it to -3 from the right-hand side. So the portion of this piecewise function, the portion of the graph of this piecewise function defined that we're going to use to find out this limit is this part. So as you can see, as we move right along with this graph, getting the x value closer and closer to -3, what happened is what the graph is going to -infinity, right? Keep on going down and down. So this is the infinity, the limit of infinity, right? Infinity limit. And then it's going to -infinity. And if we, part B, if we are looking for limit as x approaches to -3 from the left-hand side. So once again, here is -3, right? And this time we are approaching from the left-hand side. To find out the limit of that, right, we're going to be using the graph of this functions J, and we will be using this portion of the graph. Because when it's coming from the left-hand side, it will be this portion. So coming from the left-hand side, you can see that, as x value, coming from the left-hand side, closer and closer to -3. And notice that the graph is, again, going down to what? -infinity. So the limit will be, again, infinity limits, -infinity. Although the limits on this part A and then part P does not exist, it only tells you which directions are going. But however, from the left-hand side limit and right-hand side limit, they go into the same directions. So therefore, in example C, when we ask for a limit as x approaches to -3 of the function J, then we can indicate that it will be going to what? -infinity. The limit does not exist, but we do have what directions to talk about. Next, we want to look at J of -3. This is basically asking for the function value. And clearly at -3, right, when x is -3, there is no graph at all. And the graph never passed through this vertical axis, right? This is like, there is a vertical asymptote right here, right? If you go into this direction. So therefore, in this case, the functions does not define. So it's will be, I will write it down what? Undefined for the functions. Now, continuing this, we want to find out limit as x approaches to 0 from the left-hand side of what? The function J. So where is 0? Here is 0. And we are trying to talk about, what happened? We are trying to, here's 0, and we are trying to talk about what? Approaching from the left-hand side. When we come from the left-hand side, right, the portions of the part of the graph that we're going to be using is this graph part right here, right? So as we move, x value getting closer and closer to what? 0 from the left-hand side. And you can see that the function value is what? Getting closer and closer to 3 right here. And that basically means what? The function value is not 3. Again, same situations, but this time we're going to be approaching, right, the x value, right, 0 from the right-hand side. So when we approach it from the right-hand side, the portion of the graph that we're going to be using to find out the limit value is, again, the same part, this middle piece. But as we go, x value get closer and closer to 0 from the right side, again, my y value is the output value is what the graph is leading us to, what this numerical number 3 also. So from here, we can talk about the limit as x approaches to 0 for j, right? The function j, because the left-hand side limit and the right-hand side limit, they are the same. So therefore, the limit is what? 3. And that is the theorems that we talk about, the definitions that we talked about earlier. Only if the left-hand side limit and right-hand side limits go to the same numerical number, right? The same value, then we can talk about the limit exists. And what is that limit? And what about the functions? Is the functions defined at 0? Although right here is a hole, right, for this piecewise function, but I do have a closed circle right here. So that means at 0, my function value is 1. Right? At 0, my function value is 1. Now, continuing on this, next we want to find out the limit as x approaches to 5 from the left-hand side. Here is 5, approaches from the left-hand side. When we approach it from the left-hand side, we will be using this middle portion of the graph. And as we move x getting closer and closer to 5 from the left-hand side, our limit value is approaching to what? 6. So I got the limit value 6. Now for the next example, if you look at it, we are in this time, we want to get limit as x approaches to 5 right here from the right hand side. So to find out the limits of this functions, right, right hand side for the function j, we need to use this portion of the graph. And as I move the x value getting closer and closer to 5 from the right hand side, right, the limit is approaching to what? This value 4. So my limit value is 4 in this case. Again, the function does not exist because there's a hole right there, right? But the limit from the left-hand side and the right-hand side do have a limit. But however, the next questions we can answer very quickly because limit as x approaches to 5 from the left-hand side and the right-hand side, the limit values are different. So that basically indicate that the limit as x approaches to 5 of the function j does not exist because the left-hand side limit and right-hand side limits, they are not equal. According to definitions, the limit does not exist. Okay? So hopefully with this example, you sort of know how to get the limits, right, from the graph of a function. And next stop, we're gonna be looking at graphing by yourself. Next example will be graphing by yourself, and then also talk about the limit of it. So being said that, here's the next example. So this time I'm giving to you a piecewise defined functions f, and then asking us to graph this. Okay? So so the first functions, right? The first formula is a constant, which is going to be a horizontal line that basically tell us that, it will be anything that, oh, right here is a mistake. I think, this one, I meant to not 1, I meant to put x is less than or equal to -1. Make sure you change that. I forgot the negative sign right there. Okay. So -1. So it will be a constant when the x is what? Less than 1. So the constant is a horizontal line, and x is less than or equal to 1. So therefore, we will be getting a graph right here. 1 is right here, right? X is 1, and it will be a closed circle, and we will have what? A horizontal line. whenever x value is smaller than 1, negative 1, my bad, sorry. Here's negative 1, go into this directions. There you go. Okay. But the second part is x squared minus 1. So we are talking about a parabola, right? But however, this parabola shift down 1 unit, like this. But this parabola is what? Only between x is negative 1 and 1. So when I plug in a negative 1 squared is 1. 1 minus 1 is 0. So we are talking about right here, negative 1 will be 0, 1 will be 0. And since this is a parabola shift down 1 unit, so we know that this is going to be look like that. And lastly, this is negative x plus 2. So we have a slope, negative 1 and y-intercept at 2. So we are talking about here's slope, y-intercept, slope is negative 1. So go down 1, out 1, down 1, out 1, down 1, out 1, a line like this. But however, we are only interested in x is greater than or equal to 1. So therefore, here's a solid point. And then we are talking about what? Going down like this. So this is a piecewise defined functions. You know, you can use the transformation method or you can plug it in the points to draw it. But you need to draw correctly and then quickly so that you can answer the rest of the questions and finish up this problem. Okay? So it's very important on the test you graph it carefully with the open circle and closed circle so that you can answer correctly. So now for part B, we want to find out the limit as x approaches to 1 from the left-hand side. So from this graph that we draw, we are looking for x approaches to 1 right here. But from the left-hand side, so therefore I will be using what? This portion of the graph. So when I go along, x is getting closer and closer to 1 from the left-hand side, we are what? Getting closer and closer to the value 0. And then we want to talk about the next one. We want to talk about, again, limit as x approaches to 1 again, but this time is from the right-hand side. So when we are coming from the right-hand side, we will use this portion of the graph to find out. Okay? So as we move, getting x value getting closer and closer to 1 from the right-hand side, and the limit value is approaching to what? 1. So I can see that limits from limit as x approaches to 1 of the functions from the left-hand side and the right-hand side, they have different limit value. So therefore, part D is what? Does not exist. Similarly, we want to look at limit as x approaches to negative 1 this time, right here, from the left-hand side of this functions f. So that means I'm going to be using this portion of the graph to look at it. So when I go, to x, when I move the x value getting closer and closer to negative 1 from the left-hand side, then the function value is always the same. So it'll be 1. Similarly, if I want to find out the limit as x approaches to negative 1 from the right-hand side of the functions, right, f of x, then we will be using the middle portion of the graph. So when I move x value closer and closer to negative 1 from the right-hand side, the limit is what? Approaching to 0. Again, the left-hand side limit and right-hand side limits, they are different. So therefore, the limit does not exist in this case as well. So this is an example that graphing the piecewise defined function by yourself and answering all of these questions. And definitely is a test questions on this, okay? So now what we want to do is we want to look at, another type of this. Determining infinite limit. And when we are dealing with this type of problem, and you can see that, definitely you don't want to use, plugging in the number idea like we did way in the beginning, which is the numerical method, because we already see that these are basically what very shaky, because some problem you will get a limit, some problems like you will get into these situations and you will not get the limit, right? So therefore, I will not recommend like plug it in and then find out every single one, but try to get an idea and then use the descriptive form to write it down, right? So that's what I'm going to teach you, how to write it down in descriptive form and how to look at this type of problem. So let's look at the part A, limit as x approaches to -3 from the left-hand side. So what we are trying to look at is the idea of the limit that we get is x and then the functions, right? And we are interested in getting what the value of x that is approaches to -3, but from the left-hand side. So that means I'm going to try to compute that is closer and closer to 3 from the left-hand side. You can see that -3, if closing from the left-hand side, we are talking about negative, I can compute it, -2.9, -2.99. Oh no, my bad, sorry. From the left-hand side, which is going to be 3.0, 3.1, 3.01, -3.001, -3.0001, and so on and so forth. So notice that I'm getting closer and closer to -3 from the left-hand side. So what are these values? But we don't want to compute all these numerical values over and over again, because we are not interested in talking about only this case, this case, this case, and this case. Between this -3.0001 and -3, there are infinitely many numbers that we still can use. So we want to generalize it. Okay? So this is how we look at on generalizing part. For this case, we are interested in as x approaches to -3, right? So as x approaches to -3 from the left-hand side. And what we need to find out is we need to find out the value of x plus 2. And to get an idea, not to fix on one particular case, to get an idea, I can look at the numerical value and get an idea. So that means I will think about this -3.001 plus 2 divided by -3.001 plus 3. Right? Try to get an idea. So what happened is this numerical number on the numerator part, right? The value of x plus 2 will be a negative number, but it will be a small negative number, right? But it's fixed. And the reason why I don't want you to think about only one case is because this is only what plugging in the numbers, because this is only one case of many, many number that we can choose or we can approach to -3. But we can use this idea to, generalize it as x approaches to -3 from the left-hand side. The value of x plus 2, right, which is the numerator part, is a negative number. Right? And the value of denominator, which is x plus 2, x plus 3. Same thing, negative, the denominator part, the value of the denominator part, this value right here, -3.00001 plus 3, and that will be what? -0.0001. It's a very tiny negative number, right? So this is how we're going to indicate a very small, right, negative number. So we have a negative number divided by a very small negative number, So negative divided by negative is a positive, but a number, you know, a larger, if the numerator is larger number than denominator, then when we divide it, that will be what? A very large positive number. So therefore, right? Therefore, we can conclude that x plus 2 divided by x, the value of x plus 2 over x plus 3 is very large positive number. And that's what we are talking about, limit as x approaches to -3 from the left-hand side of the function x plus 2 over x plus 3. And this is approaching to what? Positive infinity. See, when we think about it, right? We think about with one particular number to get an idea of where is this going. And we don't want to use this one particular case to talk about it, because when we talk about as x approaches to -3, as I pointed out, between -3.0001 and a -3, there's infinitely many number that we can use to continue approximating. But the outcome will be what? Automatically is being able to see that it will be getting a larger and larger and larger positive value output. So therefore, in this case, we are talking about the limits will be what? Positive infinity. Now, the limit is a positive infinity. Doesn't mean that your limit exists. Okay? The limit exists. It only tells you the directions of the limit, not the existence of the limit. Because when we say the limit exists, the left-hand side approach and the right-hand side approach go to one numerical value. Infinity is not a number. And that is the part that you really need to be careful and clearly understand it. So this is the descriptive form of writing, okay, limit to the infinity case. Because you can clearly see that, you know, the function has what? Undefined, a -3, right? Now, you can also think about this idea by using the graphical methods to think about it. If you can graph very quickly your rational functions from, you know, what we learned in pre-calc. So in the pre-calc, we learned that the domain -3 does not exist, right? And the function does not define a -3, so it's a vertical asymptotes. And the numerator degree and denominator degree are the same, so it's a horizontal asymptotes right here. And then we can sort of like, you know, think about the a number that is close to vertical asymptotes, and then, you know, see which direction it's going. So that idea is very similar to the limits that we are talking about, right? So we need to talk about in general, because, you know, the question is talking about limit as x approaches to -3 from the left-hand side, approaching to, right? Not one particular value. So this is how you can generalize it and write it down, and that's how I want it on the test. Same thing, we can do the same thing, you know, on this example part B. Clearly 0 is going to be a vertical asymptote because of right here x squared. So like before, I can talk about the same thing, right? But however, this time the difference is we are looking for as limit as x approaches to 0. It's not from the left hand side or right hand side. So in order to talk about the limits of that, we need to talk about the limit as x approaches to 0 from the left hand side, and the limit as x approaches to 0 from the right hand side of the function. Only if both of the limits are the same, then we call it the limit exists by definitions. But in this case, clearly, you know, the function does not define, but we want to look at what's happened to the limit. So the same idea that we can use, right? So let's start with from the left-hand side. As x approaches to 0 from the left-hand side, So that means I can think about here is 0. Approaching from the left-hand side, that will be what we are talking about, the number right here, right? Very close to 0, negative 0.0001. So when I plug it in this number into here, let's think about it. Again, this is one particular case, but we need to write it in general, but we can get directions from this one particular case. So this is how we can state it. The value, right, of the numerator, let's start with the value of the numerator, x minus 1. And when I think about negative 0.0001 minus 1, that's a negative number, right? So it's negative a number greater than 1. So the value of x minus 1 is a negative number. And now I want to talk about the denominator part. That will be negative 0.0001 squared times with negative 0.0001 plus 2. So we want to talk about the value of x squared, x plus 2, okay, this value. So you can see that this will be a positive because of a decimal number squared, meaning decimal number times decimal number, that's an even smaller decimal number, but it's a positive. But for this one is negative 0.01 plus 2, then that will give me also a positive number. A positive number times a positive number is a positive number. Because of a very small decimal number times with another number, we will still get what, a very small positive number. Okay? So from here, I can say that the value of x squared times with x plus 2 is this is how we're going to indicate very small positive number. So now I can see that the numerator part, right, is a negative number, and denominator part is a very small positive number. So a negative number, right, which is greater than 1, divided by a very small positive number, we will get what the output will be, a very small, a very large negative number. So therefore, the value of x minus 1 over x squared times with x minus 2 is a very large negative number. So that basically indicates that this will be negative infinity. Right? I want an explanation, right? So similarly, I'm going to do the same thing when we talk about what on the positive sides, approaching to 0 from the positive side. And we are talking about that will be a very, very tiny number, 0.0001, but this time is a positive number. So when we talk about a positive number, then you can say that as x approaches to 0 from the positive side, then the value of x minus 1, and this will be still very small number, minus 1, that will be a negative number, right? Is a negative number. And the value of x squared times with x plus 2, right? The denominator part. When you square this 0.0001, that will be a very tiny decimal number, times with, but it's a positive, and times with another positive number, then it will be what, a tiny positive number. So it will be, this value is a very small positive number. So it's very similar to what we have on this left-hand side approach. So therefore, again, A negative number divided by a very small positive number, that would be what? A very large negative number. So therefore, the value of x minus 1 over x squared x plus 2 is a very small, I should say a very large negative number. So that means this will be also negative infinity. Again, the limit from the left-hand side and right-hand side does not exist, but we do have the same directions. So therefore, right? Finally, therefore, I can conclude that limit as x approaches to 0 of the function x minus 1 over x squared times with x plus 2, it has a directions. The limit does not exist, but it has a direction, which is what? Going to negative infinity, and that will be my final answer. That will be my final answer. So the last example is going to help us to look at a technique that we need to use later on. And the technique is like, something that we saw from pre-calculus, right? So this is a rational functions, and we are interested in finding out the limit as x approaches to 2 from the left-hand side of this rational functions. And like before, the previously, it makes it easier for us to determine the value of the numerator and denominator if it is in factor format. So therefore, I want to do the factoring part first before I even continue on this problem. So therefore, this I'm going to be looking at limit as x approaches to 2 from the left-hand side of when I factor it, it will be x minus 2. And in the denominator, when I factor x minus 2 times x minus 2, hey, what happens? There is a common factor that we can reduce it, right? So if I reduce in it, then it will be x over x minus 2. And I can tell you right now, and then make sure you remember that, the limits of the original functions and the limits of the simplified functions, they are the same limit. Right? So therefore, in this case, what I'm interested in is looking at what is the limits right here. So like before, I'm going to have to write it down the descriptive form to explain what is going to be going on right here. And we know that approaching to 2 from the left-hand side. So we are looking at 1.99999, like this kind of number. So now I can say that descriptive form, as x approaches to 2 from the left-hand side, the value of x, the numerator, right? Or you can say that the numerator is a positive number. And the value of, and you can write it down like this if you want to speed it up on the exam, right? Of the denominator, which x minus 2 is, but 1.99999 minus 2 is a very small negative number. So you need to indicate that, is a very small negative number. So now I can see that the numerator is positive number, denominator is very tiny negative number as we approach us to 2 from the left-hand side. So therefore, okay, therefore, x, the value of, right, I can indicate it the same thing. Therefore, the value of x over x minus 2 is a very, a positive number divided by a very small negative number, it will be a very large negative number. Right? So therefore, now I can conclude that this will be what? The limit as x approaches to 2 from the left-hand side of the functions x over x minus 2 is equal to a very large negative number, which is negative infinity in this case. So right here, what we learn is basically, we talk about, we see that limits of original function is the same thing as what limit of the simplified functions. Right? And this concludes section 1.5, and make sure you understand the limits.